Hello, welcome to this video. I'll just pick up where I left off. So the last video we were talking about the q more than 0 case, q less than 0 case, and then the case where r is sort of equals to 0. Now this part is not quite done yet. Okay, so let us just sort of figure this out. Hold on. So let's just let's just do some cleanup work for the case where r is less than 0. Then we can move on to the case where r is more than 0. So we have already here r is equals to 0, r is more than 0. So let's just finish up the r is less than 0 case. And in that case, we want to sort out the q equals to 0 case. Now, q equals to 0 will imply right here, you see, q equals to 0 will imply right here that phi will be cosine inverse or arc cosine of 0, because q here is in the numerator. So what we are dealing with here is the arc cosine of 0, and that will determine phi. Okay, my suspicion is that if q equals to 0, then you'll see that the yk for these two expressions, the yk for these two expressions will result in the same value, because let me kind of draw out why that is the case first. So we have phi equals to arc cosine of 0, and let's find that out. Okay, just as a revision, because a cos of 0. A cos of 0 is 1.57 radians, otherwise known as pi by 2. Okay, equals to pi by 2. Okay, pi by 2 is 90 degrees. 90 degrees. So phi here should be 90 degrees because it is the arc cosine of 0. That's when q equals to 0. Okay, so q equals 0. Q equals 0. Let's just write down q equals to 0 means that phi is a cos of 0. And then what does that imply? This implies phi is 90 degrees or pi by 2. So that's what we just we are discussing just now. Now, if q equals to 0, then I suppose that using yk equals to this, yk equals to minus 2 square root of minus p over 3, this cosine, equals to, it will be the same as using this expression. The more than 0 and less than 0 is more or less the same, provided that k equals 0, 1, and 2. Now let us just verify that a little bit. Okay, so what do we have? Okay, we have the 120k here, where k equals to 0, 1, and 2. So I can actually do a quick test right here. Right, I have minus 2 times, minus p over 3. I don't care what this p over 3 is here. I want to make sure that minus 2 cosine of this equals to plus 2 cosine of this. That's what I'm trying to prove. Okay, just let me write that down. I'll use my critter. Minus 2, let's see, minus 2 cosine of what? I haven't used this critter before on live presentation very much. So yes, minus 2 cosine of 5 by 3 plus 120k, right? Minus 2 cosine of 5 by 3 plus 120k. And this will be in degrees. I want to prove that this is equals to 2 cosine phi by 3. Let me undo that. 5 by 3 plus 120k. Yeah, I'm just going to write this slowly. You can fast forward if you don't want it. I'm not going to edit the videos. 5 by 3 plus 120k. Yeah, I want to prove this is the same. Of course, I can just cancel the 2's out. That will be fine. So I just want to prove cosine of 5 by 3 plus 120k equals to minus cosine of 5 by 3 plus 120k. Now phi equals to 90 degrees. Yeah. So what I'm trying to prove here is minus, pardon my handwriting. Okay. Minus cosine of what 30 plus 120k equals to cosine 30 plus 120k. For k equals to 1, 2, and 3. Okay, pardon, not this. K equals to 0, 1, and 2. Okay, so as long as I have as long as the values on the left hand side and the values on the right hand side are the same, provided k equals 0, 1, and 2, then it's totally fine. Okay, they may not be in the same order, but I don't really care. Now let's verify that using LibreOffice Calc. Okay, so let's see, 30, that's k equals to 0, right? So it's 30, let's see, let's put k here. K is 0, 1, and 2. So I'll have 30 plus 0 times 120. Okay, and let me do a quick fix with this. I'll lock this. So it's 30 plus k times 120. That's what I'm saying here. Now let's do this. 30, 150, and 270. So there are 3 angles we want to take into account. And let's do the cosine and minus cosine of that, just to be sure. Equals to cosine. Okay, so this is in radians, right? This is in radians. So I need to times, so I need to take this number in degrees times pi divide by 180. So that's how I convert from degrees to radians. And of course, I forgot my little bracket right here. Okay, so this is the cosine of one of them, right? And 270 here should be almost 0. And let's do this as well. Oops, I totally forgot. I should be changing this this to here. Cosine of C5 times pi. So I have a negative cosine and a cosine right here. All right, I need to change this to a minus. Minus. Okay, minus, and here's also a minus. Now, what do we notice here? Okay, cosine of 30 is equals to minus cosine of 150. So that's the first value, right? Cosine of 150 equals to minus cosine of 30. This is the second value. Cosine of 270 equals minus cosine of 270. Both of them should be 0. As you can see, this is minus 1.83 times 10 to the minus 16. This is 1.83 times 10 to the minus 16. Essentially speaking, both of these are actually 0. So it doesn't really matter. Okay, this should be close to 0. So cosine of 270, right? Cosine of 270 is 0. So what's the exact value of 270 degrees? So this is pi by 2 plus pi, right? So it's 3 pi by 2. So let's try cosine equals cosine 3 times pi by 2. Okay, so this is almost 0. I think it's a round off error, but that's okay. So cosine of 270 should be 0 because cosine of 90 is 0. That's how the cosine wave actually goes. If you remember, let me. Okay, never mind. I think this is quite fundamental. I'm not going to do anything here. Okay, let me just delete this. Oops. Let me yes. So this part is proven, and since we've proven this, it doesn't really matter which formula I use, right? I could have q less than 0, q more than 0. Both of them are fine. So what can I do? I can just copy and paste this here. I'll just use the q less than 0 case, and then I will just paste over the to do here. Okay. So both of them are the same. I can get yk either way. It may be, again, you saw just now, it will be in different order, but that is okay, completely okay. So long as you get all three values of yk, then that is fine. Okay, so that's the case where q equals to 0. Okay, now now we'll just move on to other things. All right. All right. Now let's program the case for r equals to 0. Okay, r equals to 0, then we will expect 3 real roots. Okay, we will expect 3 real roots. Okay, at least 2 of which are equal. Okay, so what are the roots here? Okay, we have the yk, okay, which is y1, y2, and y3. You have xk as well. How do I program this? Yeah, so let's see. So let's do the r equals to 0 case first. Then we'll sort it out bit by bit. See, r equals to 0 case, I mean r more than 0, or r equals to 0 or r more than 0, then we will not really need to sort things out by q, as you can see here. We will need to actually calculate a and b. Okay, we will need to calculate a and b. So let's calculate a and b. So maybe I do not need xk and yk, right? I do not need xk and yk. I don't even need 5 for that matter. I may not even need 5. Alright, I have not. Yeah. Actually, hold on, let me see this. Yes, actually, I think I missed something. Okay, find cubic roots. Right. I have not even done my r less than 0 case yet, if you noticed. So yeah, pardon, it's a bit of a mistake on my part. So yes, I have not even done the r less than 0 case. So let me finish this up before moving on to new things. Right, let's do that. So let's do y1, y2, and y3, because that's what we want to find out. Okay, so r less than 0, we have 3 real roots, right? R less than 0, we have 3 real roots. So let me just bind the values. Y1, let y1, what should it be? Is a f64 value, right? Okay, y1, y2, and y3. Okay, I'll have 3 float 64 values. Okay, so y1, y2, and y3, in the case where r less than 0, will be all the formulas we've been trying to work out just now. So so this is the get yk function. Okay, get the get yk function. This should in turn rely on xk. I mean, xk is here, right? Yeah, xk is yk minus b over 3. Ah, yes. Xk equals yk minus b over 3. Yeah, so we'll need y1, y2, and y3 first. Right, we need y1, y2, and y3 first. So let's just calculate y1, y2, and y3. So where is it? Yes. Yeah, here is our phi in degrees. We already got that. So let's get our y1, y2, and y3. Okay, y1. Okay, let's do this, or rather not y1, y2, and y3, because yeah, y1, y2, and y3 was because I thought I misremembered. I usually start from 1, but k here starts from 0, and since this is yk, this should be y0, y1, and y2. So let's change that. y0, y1, and y2. That's what we are trying to find out. Okay, so let's go back down here. Okay, things are getting a bit long. The longer the program is, the more sort of, confusing things get. So yeah, organization is important. Okay, well, let's do this. y0 first. Okay, y0 equals to what? Get yk, right? I need to get yk. K is 0. What is p? Yeah, what is p? Totally forgot. Yeah, p should be here. Yeah, p is here. Phi is here, q is here. Yeah, I think that should be fine. Okay. And let me open the terminal, and I do cargo run go watch -x test. Yeah, this should build things up nicely. If everything goes well, this should not cause an error. Yes, this shouldn't cause an error. So let's do y1 as well. So k here equals to 1. Okay, that's y1, and then I will have y2, where k equals to 2. So now I have y0, y1, and y2. Excuse me, y0, y1, and y2 for k equals to 0, 1, and 2. Okay, so let's see. I think I should substitute here phi in degrees, right? Phi in degrees. Phi degrees. Phi degrees. Because that was the expected correct unit. And this should be, I'm going to change this, yeah? I'm going to change this to degrees. So let's see whether I can rename symbol phi degrees. Yeah, so all of this should be 5 degrees. Not the number 5, but PHI 5. So y1, y0, y1, and y2 are done. Okay, and I guess I don't want to cram in my getXk function here. I'll do the getXk right at the end after I get my y1, y2, and y3. So let me put this here. All right, I'll do it like that. Okay, so the last step is to get the xk. All right, so we have the case for r less than 0. Now let's go to r equals to 0. So I'm going to get rid of this xk and yk first. Let me do a calculation of a and b. Okay, so yeah, we don't need phi in this case anymore. So I'm just going to delete a lot of this. And then we honestly don't even bother about q anymore. So let's delete the q. Okay, this is not important in the r equals to 0 case. So the r is more than or equals to 0. Then we need to calculate a and b. Let a, let b. Okay, I'm going to copy and paste it into the r more than 0 because I suspect the calculation procedure for r more than 0 and r equals to 0 is pretty much the same. And actually, if that's the case, I can just change the sign to as such. Let me see whether the greater or equals to 0 actually works. Okay, maybe the greater or equals to is supposed to be like that. Yeah. So it's greater or equals to 0, right? Okay, never mind. Let me just leave it as this. And it's asking for type annotations. I need this to be both F64. Yeah. So these are doubles. 14 down. Okay. Let me just do the R more than 0 case first. Okay. If R more than 0, expect complex roots and one real root. Okay, we are not interested in complex roots, so I'm not going to bother with them. Okay, I'm not going to bother with them. I'm only interested in the one real root. Okay, I'm only interested in the one real root in this case. I don't want to do the complex number. Right, so let's just do the one real root. The one real root is getting a plus b. So this is a and this is b. So let's see what do we need here. We need a q over 2. Okay, we need q by 2. So q has already been calculated, so we don't need to calculate that again. Okay, let's have a r more than 0. Q has already been calculated. So I need a minus q by 2 plus r. And the minus q by 2 minus square root r, should be square root r. Alright, so let's see. Let q by 2 equals to minus q by 2. Yeah, this is a bit of a cumbersome way to do it, but I'm just doing it like that. Okay, q by 2.0. Okay, let minus q by 2 is this. This should be F64. Okay, so we have the minus q by 2, then we have a plus r and minus r. So, oops, let's just do that. So a equals to, okay, minus q by 2 plus r dot square root. And then I want this to be a cube root, CBRT, cube root. So let me see what this is. I hope it's actually a cube root now. See, there's a cube root of a number. So you just hover over it. CBRT is cube root of a number, so it returns the cube root. So good thing these things are here, so it makes life easier for us. Okay, let's do the same thing for B. I'll replace this with B, and as you can see, b here should be a minus square root r. So let's get the minus square root r here. Okay, so now a and b are calculated. I just need my y1. Okay, or rather, maybe this should be y0. Yeah, y0. y0 equals to a plus b. Okay, very simple. So I need to calculate the real roots. Okay, real root other roots y1 and y2 are imaginary. Okay, so I'll just leave it as that. So y0 is the real root. Now let us calculate the r equals to 0. Now again, if r equals to 0, okay, if r equals to 0, then a equals to b, because square root of 0 minus q by 2 plus or minus square root of 0 is still 0. So let's do, I'll just copy most of this code over. Okay, I'll copy most of this code over, except I will just delete the r square root here, because that's kind of redundant. Yeah. So it's minus q by 2, and you do a cube root. So let's see. So the first real root is just a plus b. The other two equal real roots. Okay, two other equal real roots, right? Two other equal real roots, what are they? Minus half a plus b and minus half a plus b. So y1 equals to minus 0.5. And what's a plus b? A plus b is just the y0. Yeah, in over here I use y1, but it's actually y0. So maybe later I can change the nomenclature. All right, so these are the two equal roots. I'll need to put my semicolons there, and there you go, y1 and y2. And okay, I forgot my times. Okay, and there you go, y1 and y2 are now calculated. So since we have y1, y2, and y3 more or less calculated, I should be able to get my xk. Okay, so well, the thing is here, y0 is, yeah, it's a little problematic. We have two cases here. Okay, we have two cases here. One is that we have 3 real roots. The other is that we have only 1 real root. So how are we supposed to represent that? Okay, how are we supposed to represent that? So well, find cubic roots should have some sort of some way to tell us, you know, let's see, yeah, to tell us that, hey, we only have 1 real root or we have 3 real roots. There are some ways we can actually deal with this. Okay, one of the ways is that we actually return a vector of f64. So this vector of f64 means you can return 3 f64 values, 3 float 64 values, or 1 float 64 values. Okay, that's one way of doing it, and that is definitely the simplest way. Okay. Okay, so that's one way of doing it, but I personally prefer one other way. It's called the option way. Okay, so okay, never mind. Let me do the simpler way first. Oh, this is getting late. Yeah. Let me do the simpler way first. Okay, so we will get x. Let's do x1, x2, and x3. Let x0 equals to get xk. Okay, first I get y0 and b. Okay, that should be fine, except that well, we have to return this into the vector, right? Let result vec, okay, solution vector equals to vec, use the macro here, x0. So this is how you instantiate a vector. Okay, then I'm going to return the solution vector here. Okay, this is the simplest way to do it. Okay, so this is at least us getting one of the roots already. Okay, but we need to have other roots as well. We need to have other roots as well, because there's sometimes a y1 and y2, right? y1 and y2 are sometimes defined, sometimes it is not defined. Okay, because as you can see here, in the else case, if r is more than 0, when we have imaginary roots, then y1 and y2 are not defined. Okay, so they are like null values, right? Null values. Okay, so that's problematic. Okay, so y1 and y2 are, in this case, we are not interested in imaginary roots. So y1 and y2 are undefined. Right? So how do you so-called check if y1 and y2 are undefined? Right? So okay, y1. Yeah, so what you do is maybe you do if y1 equals to, I don't know what, a null value. Yeah, that's how you do it in some other languages. we don't want to do that. Okay, so the trouble with y1 and y2, okay, let me write this down. The trouble with y1 and y2 is that sometimes y1 and y2 are undefined. Okay, this is the imaginary root. Okay, let me put this up here. Maybe that makes more sense. The trouble is with y1 and y2 is that sometimes y1 and y2 are undefined. We call this imaginary. Okay, so how do you tell the code? Yeah, how do you tell the code? Sometimes I want to define y1 and y2. Sometimes I cannot define y1 and y2. So the most basic thing is to use this thing called an option. All right, option. Now, so I'm not going to bring this up. Okay, option in Rust. Okay, this is one of the most important ways you tell Rust. Sometimes the value exists, sometimes it doesn't. So for example, this is the divisor divide code. This is the example they give. If you divide something by 0, then this is undefined. Yeah, undefined. Right? So this is what you would use to say, okay, sometimes this y1 and y2 are defined, sometimes it is not. We use this option enum. Let me demonstrate to you. Maybe there will be some clarity. Okay. So y1 and y2 are, well, y0 is always, all right, always going to be there because you always have one real root, but y1 and y2 may or may not be imaginary. Okay, note that y1 and y2 may or may not be imaginary. So if it's imaginary, then we do not define them. If it's real, then we need to define them. So to sort of tell Rust, or to sort of express this fact that sometimes y1 exists, sometimes it doesn't, is to use this option enum. Okay, enum is we call an enumerator. Yeah, enum, Rust enum. Okay, this will be your first time, one of the first time you encounter an enum. Okay, so an option is just one type of enum. Okay, but again, it's kind of abstract now, so just let me try and finish this up. So the option enum has well, the option enum is basically our way of expressing that, hey, sometimes y1 exists, sometimes it doesn't. Okay, so when it exists, what do you have? Okay, you actually use this none keyword, the none keyword, to tell it, oh, this y1 does not exist. Okay, so how do you tell that? Yeah, you will say here y1 equals to really literally none, y2 equals to none. Yeah, that's all you are saying. Okay, none is one of the variants of option, because there are two choices of options. The option using the option enum basically says, hey, this variable might exist, this variable might not. So if it doesn't exist, we use the none keyword here. If the variable exists and there's some value, we use the sum keyword right here. Okay, so this is the none keyword saying that, hey, y1 and y2 are imaginary. I don't really bother with the values, so just, don't bother me at all. I don't want to deal with it. So that's the none. That's what none is saying. If y1 and y2 exists, then yes, there's a real value. So instead of none, we will use the sum keyword, or the proper name is called the sum variant. Okay. Okay, so I'm gonna say here, we use the sum variant for the option enum to say that, hey, y1 and y2 exist. And in contrast, right here, we use the none variant of the option enum to say that y1 and y2 do not exist. Now, okay, so enums are another subject altogether that we will need to revisit. Okay, we will need to revisit because it's a bit hard for me to squeeze all the things here. So maybe following coming videos, we will have to discuss enums eventually. But let me finish this code first. Hopefully you understand what's going on here. Yeah, you have a case where there is some value of y1 and y2. There's a case where there's no value in y1 and y2. Okay, and then again, here we have y1 and y2. We need to encapsulate. We need to put this value of y1 and y2 in the sum variant of the option. Okay. So now y1 and y2 are all here. So right, we have a solution vector that returns one of the roots, which is great. Now I will have to say, hey, if this y1 and y2 are none, then we do not add anything to the solution vector. That means we only have one real root. If there is some value, y1 and y2 have some real value, then we need to add that value into this solution vector. So how do we do that? Okay, so instead of using if statements, Rust has something called a match statement. So let's do a match statement. So match statements are used with enums. Okay, so we need to revisit this, but let me just give you an introduction to what that looks like. So match y1 is right here. So y1 is that enum we were talking about. It's an option enum, specifically speaking. And let's see if we can let's see. Let me see if we can do a is there a code action here that can hold on. Alright, so actually I was looking for the quick fix. I kind of forgot where that was because I haven't used VS Code in a while. But yes, I'll use a quick fix. We'll use one of the quick fixes right here. And this will be called fill match arms. Yes. So in the case that there is some variant, that means there is a value here. There is a y1. If there is a y1 value, just call this the y1 value, right? Then we will actually want to append it to the vector, right? Okay, so solution vector. Okay, what do I do with the solution vector? I want to push a value, right? I want to push the value, and the value is called y1 value. Okay, and that's all. Okay, and it's going to give a problem because the solution vector is not mutable. We need to make the solution vector mutable. So let's make the solution vector mutable. Let mute solution vector equals to vec x0. If y1 has a value, solution vector will push the y1 value. If there's a none, if there is none here, I will not do anything. So to do that, you just use the two brackets there. That's basically the same as to do nothing or void. Okay, void. So what is this saying here? I am matching, I'm doing pattern matching, or it's like an if statement, but it's better than an if statement, right? So it's just like an if statement. If this option happens to be a sum value, a sum variant, they call it, sum variant. So yeah, if y1 happens to have some value here, and the value of y1 is this y1 value here, I will push this y1 value into the solution vector. Oh, I think something is wrong. I should actually get the x1 value. So I should get xk. I will do the y1 value and b. So yeah, That's getting the xk right here. So this is the correct one where you push the x value into the solution vector, right? And then I will need to do the same thing with the y2. Okay, match y2. So in the case that there is a real root, y1 is a real root, we will get the xk from this y1 value or x1 and we'll push it to the solution vector, right? So the same thing here. Okay, if that right, sorry, I should explain the other one. If y1 happens to be imaginary, we already said that okay, we will not have no value here. We will just do nothing. By doing nothing, we use this 2 bracket sign here to indicate that we are not doing anything. So I'm going to do the same thing here, y2, match y2, and I'm going to do a quick fix to match all the arms. So again, y2 value, all right? And let me do a quick fix here. Oh, I can't. Let's see whether a refactor will do. Okay, add braces. Yes, I like the add braces one because it does this for me. Adds the curly braces for me. So I'm going to do the solution vector and I'm going to change this into the y2 value. Okay, push the y2 value. Otherwise, don't do anything. Same thing. Oops. There you go. So can you see what this code is doing? Yeah. So right, we have gone through a lot in this video. Basically, oops, I hope it's not too loud. Yeah, better not speak so loud into the mic or increase the gain too much. But anyway, we were trying to find the values of yk. Okay, we are trying to find the values of yk. So here's the get yk, right? If r happens to be more than 0, or r happens to be less than 0, yeah. If r happens to be less than 0, then we get this yk, right? The yk is gotten like that. So we have the 3 real roots case. So y0 is well, we will just get yk where k equals to 0. We get all the degrees, we did everything according to the formula, and we have 3 real roots here. Okay. Let me I think there is an error right here. Expect complex roots and 1 real root. Okay, I made a mistake. This r more than 0 we should not. If r is more than 0, we should only expect 1 real root. So this is the equal root. This should actually go right here. Okay. Kudos to you who actually spotted this early on. Good job. I didn't spot it till now, but here it is. Yeah, so A is F64, B is again. A is F64, B is F64. This is for the case where R is more than 0. We expect 2 complex roots and 1 real root. So the only real root right here is defined by this A and B. Y1 and Y2 are none because I do not want to care about imaginary roots. Else, we expect 3 real roots, 2 of which are equal. A and B are defined as such, and the 2 real roots y1 and y2 are defined by this sum type of this option enum. Okay, we'll have to revisit enums again. It's probably quite confusing to you right now. So if you've never touched enums before, so we'll deal with that again with some other examples, or just try and revisit it. Okay, so yeah, so we got the y1, y2, and y0 for all the cases. Okay, and of course some of them are imaginary, some are not. We use the option enum to sort of represent that in programming, Rust programming language. So once we got the y1, y2, and y3, or y0, y1, and y2, we get the xk. So we'll always have a value, the x0 value, that's the one real root that always exists. So the solution vector is a vector with this one real root. Okay, if y1 if it happens to be real, then yes, we push it to the solution vector. If it's not real, then you do nothing. Same thing for y2. So if we have the two equal roots, we will have three of these what do you call that? Three of these values in the solution vector. Okay, so this is the simpler way to do it. Of course, we can actually return option enums in the solution vector. That's another way of doing it, but let's not overcomplicate things now. Okay, so I want to test the code, right? I want to test the code right now. So let's save. Let's save this. And yes, where do I test this? Where do I test this? Okay, maybe let me make a test here. Right. Okay, test function test 3 real roots. Right? Let's have a 3 real roots test. Okay, it is not running because I forgot to add my brackets. Yeah, it's too late at night. Okay, so here's the 3 real roots one. Let's see. Cubic roots test 3 real roots. Yes, so this is this test right here. Okay, so let me do this. Okay, so what is this? B, C, and D, right? This is the normalized version of the roots. So A is the what do you call that? Right, A should be 1. That is the so-called value. Right, this is the coefficient of the x cubed term. It should be 1. So B, C, and D are the coefficients of x squared, x and the constant respectively, or x to the power of 0. So B is 0, C is -7, D is 7. Okay, so let's try that. Okay, so find cubic roots. Let solution equals to find cubic roots of B, C, and D. So what's B, C, and D? So I want to write here x cubed minus 7x plus 7 equals to 0. That's what I'm trying to solve. So B, C, and D, let B equals to 0, 0.0. Let C equals to -7, 7.0. Let D equals to 7.0. Let's find the cubic roots. Okay, find the cubic roots of B, C, and D. Okay, let me do a... I just want to... or maybe do debug. dbg solution. Let's see what happens. Alright, I'm getting lots of warnings, but I can't see anything here. So maybe I'll just use the panic, yeah? Panic. Okay. Okay, solution, and let me use this I'll just follow the compiler. I just want to see what the results of the solution, what they are. Oh, let me use a different format string. They are suggesting using the question mark here. So the question, colon and question mark right here. All right, so what's this say? Okay, it panicked at this. All right, well, look at the roots now. -15, -382, -748. So something's obviously wrong. we will need to do some debugging. This is why testing is very important. Okay. But yeah, I think that's at least getting us somewhere there. We have programmed some things, some of the logic in, and that's encouraging. However, we have a lot of work to do right here. Okay, so we'll need to find out where the bugs are. This is very normal part of programming, especially this late at night. So my brain's my brain's not working as efficiently, but this is how pretty much you want to do your programming process. All right, so I think that's enough for today. That's way too long a video, but I hope this was interesting and helps you to understand programming in Rust a little bit better.